Welcome back. This is the session 3 from EasySpin Academy 2020. In this session, we'll now do our first EPR spectral simulation. EasySpin's spectral simulations is our grouped by different regimes. And in order to see this, let's go look at the documentation. If you go to your documentation, you will see that there's a large section on spectral simulations, and most of them are for continuous wave EPR. There's some general experimental parameter considerations, and then there's a specific function for the isotropic and the fast motion regimes. That function is called garlic. There is a function for slow motion regimes, so when a radical is in solution but doesn't tumble fast enough to average out only anisotropies, and that function is called chili. Then there is a method for trajectory-based simulation dynamics, and then a very important function called pepper that allows you to simulate solid-state EPR spectra. So depending on the state of your sample, you have to use a different function. Pepper for solids, garlic for liquids, and chili for the in-between regime where your center is just moving very slowly. In this session, we talk about garlic. Garlic is the function for the isotropic limit. So if the molecule tumbles really fast, so everything averages out and you get just a series of sharp lines. Okay, let's start out. Clear, I always do clear to clear out the workspace of any leftover variables that might interfere with what I'm doing. Let's define a spin system for a simple radical. Sys.g equals to, let's say 2. And we'll also define, if you want to simulate an EPR spectrum, we also have to define a broadening, a line width. Now there's different ways of specifying how to broaden lines. And the first and simplest one is just a convolutional broadening. That will just mean that EasySpin will simulate a stick spectrum of where your resonance line is and just broaden that stick spectrum with a specific line shape. And to do this, use sys.lwpp. Now LWPP stands for line width, peak to peak. And you can give 1 or 2 numbers. If you give 1 number, it's the Gaussian. It's a Gaussian broadening. If you give 2 numbers, the second number will be the Lorentzian broadening. Okay, so that's all we need for a simple radical signal. We need the G value and the broadening. That is all up for the sample. Now, the experiment. The experiment is a separate MATLAB structure, and the conventional name for it is exp. But you can name it any way you want. And the only thing that's needed for a basic simulation is the microwave frequency. You need to tell EasySpin whether you're at X band or Q band or W band. And to do that, write MW fric equals, and then let's say 9.5. This is in gigahertz. So all microwave frequencies in EasySpin are in gigahertz. Again, I want to remind you to be careful about your spelling. There's an uppercase F, lowercase mw. If you don't spell it this way, EasySpin will not recognize the input. So finally, what we need to do, we need to call garlic, which is the simulation function, and supply it with information about the sample, the system, and experiment. Let's put a semicolon at the end. Now, if you don't ask it for any output, and if you run this now by pressing Control Enter on Windows or Command Enter on the Mac, you should get a simulation and a plot. And as you can see, we get a label plot with the resonance line with a certain width, and if you look at the width, it is going to be exactly 0.3 Gauss, 0.3 millitesla peak to peak. So from the maximum here is at about, what does it say? I have to zoom out. Anyway, so it's 0.3 peak to peak. Magnetic field units in EasySpin are millitesla. So to remind you that 1 millitesla equals 10 Gauss. So it's a very easy conversion if you use to Gauss to get to millitesla. And as you've seen here, garlic was able to find the field range automatically. It shows a field range that nicely accommodates the full spectrum, plus a little baseline left and right. Garlic is generally able to do that, but other EasySpin functions might not be able to figure out in advance what the appropriate field range is. In the general case, you actually have to simulate the spectrum in order to know how it looks like. But for simple spin system, there are some heuristics EasySpin applies to determine a field range. It might not be quite on sometimes. So in those cases, I recommend just specifying your own field range. And we'll get to that. So how are we going to specify a field range? Well, what you can do is you add another field to the experiment structure, exp.range. That specifies a field range. You have to provide two numbers, the starting field, let's say 315 millitesla, and the end field, 355. So the lower and upper limit. And then these are in milliteslas. Okay, if you run this now, we'll get the appropriate field range, and the line is still at the same resonance field as it was before. It looks narrower because now the field range is much larger. There is a second possibility to define the experiment range. I'm just going to comment this out. And the second possibility is to use a center and a sweep, a center field and a sweep range. EasySpin takes this with a field center sweep, and you have to give two numbers. The first one is the center field. Let's say, what is it here? We can zoom in. So if you mouse over your figure on the top right, you will have a little menu that pops up. There's a zoom in button, and if you zoom in, we can see the zero crossing of the line is about 339.3. So we can center our field at 339.3 millitesla, and maybe just do a 5 millitesla sweep width. Okay, and now you see we're nicely centered. If you happen to specify both a range and a center sweep, then EasySpin will tell you, if you run this now with Control Enter, it will actually tell you that it's using exp centers field and it's ignoring the range, exp range. When you measure an EPR spectrum, you also have to specify, or typically you know the number of points you acquired. Either you specified it or the software chose it for you automatically. EasySpin typically uses 1024 points by default, but you can change that default depending to what you need. So for example, we can now add, let's remove the center sweep again and say exp endpoints equals 70. Endpoints is the field that you need to give. And then semicolon to suppress output in the command window. You can run the whole thing by pressing Control Enter. And now we're getting an error. Now it's telling us that the Gaussian line width is smaller than the increment, and it cannot perform the convolution. It means that your line width is so narrow that the whole line falls between two field increments. So what you need to do in this case, you need to increase your number of points. Let's go to 500. And voila, that worked fine. And so that is an important point that people sometimes run into, that their field resolution is insufficient to accommodate the very narrow lines they're trying to simulate. Okay, that is about the field range and the number of points. Let's briefly look a little more about the convolution, at this convolutional broadening. First, I'm going to narrow the field range a little bit more so we can actually see what's going on. I'm going to zoom in by narrowing the field range. Voila. So now we've got a nice zoom in onto the spectrum. Now let's modify the line width broadening. So this is the Gaussian broadening, as already said, of 0.3 millitesla, but we can make it a Lorentzian broadening by making it an array of two numbers. The first number being the Gaussian broadening, peak to peak, and the second number being the Lorentzian broadening. So in a way, Gaussian peak to peak and Lorentzian peak to peak. And of course, I'm sorry, what did I do here? This is as always in millitesla. If you run this whole script now I'm gonna run all of this here, but just pressing Control Enter, we'll see now that the line shape changed. We get a Lorentzian line, which has much more extended wings that go out pretty far. You can also combine the two, and actually let's make plots. Before we do that, let's just generate a plot. We're going to ask Garlic to not plot the spectrum, but actually return it to us in two variables, B and spec1. This will instruct Garlic just to skip the plotting and just store the simulation results in these two variables. And let's actually make a nice comparison here. Let's put the experiment on top, just for right order. Let's first simulate a Lorentzian spectrum. Let's call it spec L because it's for Lorentzian. And then copy paste this and just change it to a Gaussian and call this spec G and plot the two at the same time. Plot B comma spec L comma B comma spec G. This way we're plotting two things at the same time. And voila, here you can see it. In the plot you can see that in blue that's the Lorentzian line shape, and in the red there's a Gaussian line shape. We can add a legend to this figure. Legend, so the first one was Lorentzian broadening, the second one was a Gaussian broadening. The command is legend. And if I run the whole section again with Control Enter, it should be adding the legend, which now shows up in the top right corner. But you can move that around and you can configure it, have no frame and so on. But one thing of note here is that the Gaussian line looks more intense than the Lorentzian line. And so how does EasySpin actually determine the intensity of a spectrum? Well, in EasySpin, every simulation of a spectrum assumes the same number of spins, right? Now, the Gaussian line is much narrower than the Lorentzian line, right? The red curve does not extend as far out. So if you would do the double integral, which is what the procedure you would use to determine the number of spins, these two spectra actually would give the same number. But because the red spectrum is narrower, it will be taller. So that's an important thing to keep in mind. EasySpin is quantitative in terms of the number of spins. So if you have two very different spectra from two different spin systems, they're always referring to the same number of spins. An important caveat though is that EasySpin only simulates unsaturated spectra, right? So if your experiment is such that your microwave power was too high and you saturated part or all of your spectrum, then you can't quantitate the spin anymore, and also EasySpin can't properly extract the number of spins from that. Okay, now what if you have a mixture of a Lorentzian and a Gaussian? We can add that as well. We're gonna copy these two lines, put them here, and now just split the 0.3 up between a Gaussian and the Lorentzian with 0.15, 0.15 each. Let's call this spec of the mixture and add this to the plot. B comma spec M. If you run this, we see that it's kind of in between. The intensity is reduced. We have a little bit of the outer wings in the yellow spectrum, but we also have the fairly sharp peaked shape at the center of the line. So that's how you specify Lorentzian broadening. If you want to rescale and want to plot them on the same scale and scale them to the maximum, all you need to do is just divide each spectrum by its maximum. So spec L divided by the maximum of spec L. So that will give a rescaled spectrum. Spec G divided by the maximum of spec G. And spec M divided by the maximum of spec M. And then Control Enter. And voila. Now you can clearly see that the shapes are indeed different. If you're trying to follow along by typing and you can't catch up, don't worry. We'll provide all these scripts, including solution to the exercises afterwards. So for now, probably it's just easier to watch along and take notes, take side notes for yourself. Okay, an important thing to mention is when to use sys.lw versus another line with broadening parameters called sys.lw without the pp. So the first one is the peak-to-peak broadening. And that is very useful if you're running or simulating a continuous wave EPR spectrum, where you really, the visual quantity is really the peak-to-peak width. So this is good for CW EPR. If you are simulating an absorption spectrum, let's say that's something you measured in a transient EPR or pulse EPR experiment, then it's better to use LW, because that uses the full width to half maximum for the absorption spectrum. And that's something that's easier to read off in an absorption spectrum. So you have two different ways of specifying convolutional line width broadening, and you can't use both at the same time. I think EasySpin will either tell you it prefers one over the other, or he will just give an error and says, just give me one of the two. So that is convolutional broadening. Next, let's add some hyperfine couplings and some nuclei. So we're going to clear out the figure with CLF. We're going to clear the workspace. So right now, let's look over to the workspace. We've got the series of variables defined. If you start a new kind of modeling or a new little job, always clear your workspace. That helps you avoid any interference from previously defined variables. Okay, organic radical with G equals 2. Let's now add 1 proton, nukes, 1 H. Let's add a hyperfine coupling of 100 megahertz and add a convolutional peak-to-peak Gaussian line width broadening of 0.1 millitesla. Let's specify the microwave frequency for the experiment. Let's say 9.6 gigahertz, and let EasySpin choose by itself what the field range is. Okay, so now if you run this, we're getting a spectrum with 2 lines, split by about the equivalent of 100 megahertz in millitesla. Okay, so that's as simple as that. And you can just keep adding protons and also adding hyperfine couplings. I'm just adding one more here. And then you get more and more of these hyperfine splittings. Now, if you don't specify a line width, so let's say the line width to 0, what will happen if I press Ctrl Enter? Gaulic simulates just a stick spectrum. Now you can see that it's an absorption spectrum, so the intensity is positive, and you just get sticks at the resonance positions. And this kind of shows you what Garlic does, or EasySpin in general. It first simulates a stick spectrum and then convolutes each stick with the desired line shape to give you the final broadening. That is the simplest broadening model. There's other broadening models we're going to talk about later when we get to solid state EPR. Okay. Next, what happens if you have equivalent nuclei? I guess let's go back to one nucleus here. Actually, let's copy this section. You can always copy a section down here. Let's go back to one nucleus and say we've got one with let's say 30 megahertz coupling. Especially in organic radicals, let's add a little line width here, 0.5 millitesla. Voila, that's too much. 0.2. Voila. In organic radicals, often you have the electron spin is coupled to a series of protons, and if the symmetry of the radical is high, couplings to some of these protons might be identical. Right? And for liquid state EPR, you can tell EasySpin about that by saying sys.n and then giving the number of protons or nuclei that have that specific hyperfine coupling. So for example, if there are 2 hyperfines, 2 protons with a 30 megahertz hyperfine coupling, you just say n equals 2. Okay, and if you run this, voila, you get a spectrum with the expected 1 to 2 to 1 ratio. If you have 5 of them, you get this way, and if you have 50 of them, you get a spectrum that looks like this, and if you have 100 of them, you get an error. And the errors, always, if you get an error, it's going to be red. I'm going to clear this out again so you can see it. An error always prints in red in a command window. And there's always a lot of debugging information, but the second line typically is the error message. So what EasySpin actually found wrong. And here it says that the Gaussian line width is smaller than the increment and cannot perform the convolution. So again, we have the situation where the lines are so narrow or the field range is so wide that the resolution is not sufficient to catch each line. what we need to do in this case, as before, is increase the number of points, endpoints. X.endpoints equals, and I'm going to put in like 10,000 points. See if, or maybe 50,000. That should definitely be sufficient. So if you run this with Control Enter, voila, we get a spectrum now. This is a spectrum of 100 protons. And you know, if you go again, if you zoom in to the tails, you'll see there's a lot of peaks that you will probably have a hard time measuring in an instrument because you require such high signal to noise ratio. Okay, so this is how you specify multiple equivalent nuclei. Let's increase the hyperfine coupling actually, let's say to 100 megahertz. Notice the spectrum here, it looks fairly symmetric, right? Now if you go to 100 megahertz, what you see is we're slowly getting into a regime where things are not entirely symmetric anymore. And the reason for that is our second order effects, which EasySpin automatically takes into account. So you don't have to worry about that, it's all taken care of under the hood. If your hyperfine coupling is large, second order effects are included. Okay, now next topic that we briefly need to look at are harmonics. As you know, typically CW EPR just measures the first harmonic, but EasySpin allows you to basically specify which harmonic you want to simulate. Let's just clear everything out and then clear the figure. Start with a spin that's a 31 phosphorus, let's say, with a coupling of 40 megahertz as usual, and some line width broadening of, let's say, 0.1 millitesla. Okay, I'm not specifying sys.s. I could, but if you don't give sys.s, it's automatically assumed to be sys spin 1/2. Okay, let's now give the microwave frequency, let's see 9.3, and then an exp harmonic, specify the harmonic. We can start with 0 and simulate that, asking Garlic to return us the simulation. And then we can copy and paste this and just simulate the first and the second harmonic. And we could plot this all in the same plot, or we can make 3 different plots. And let's do that. The command for that is called Subplot. This is extremely useful. It takes 3 inputs. The first 2 lay out a grid of plots in your figure. And if I type 3, 1, it means we have like 3 rows and 1 column of plots. And then the third number tells us is the index of which plot you want to plot in next. So 1 will indicate you want to put it in the first plot. What we're going to plot there is going to be in spec 0. Okay. And let's copy this twice and just increment the plot index and the spectral index that we simulated. We're going to call this spec 1 and spec 2. So the code is a little repetitive, but it's kind of short enough that it's not worthwhile writing a for loop or something. Okay, so if you run this, we get 3 spectra plotted on top of each other. You can say 3 subplots, 1, 2, and 3. And the top one shows the absorption spectrum. The second one is the first harmonic. And the third spectrum here is the second harmonic. So all you need to do is set exp.harmonic. And it might be, this is often very useful because if you know, I personally prefer to look at absorption spectra. They're much more intuitive than derivative spectra that are typically measured. And in EasySpin, it's easy. You just set the harmonic to 0, and when you then later want to do fitting, you set the harmonic to 1. So that brings us to field modulation, right? So the fact that we're seeing this first harmonic is a result of applying field modulation during the measurement in the spectrometer and then doing lock-in detection at the first harmonic. Let's do the field modulation. EasySpin lets you specify the field modulation automatically. So I'm going to copy everything down for our sample and the microwave frequency. And now I'm going to just simulate the spectrum just for ourselves. Voila, 2 lines. They look all good. Now let's add a modulation amplitude of, let's say, 0.1 millitesla. Again, this is millitesla. This is gigahertz. This will apply an actual field modulation, and that then really corresponds to what you do experimentally. Before, in the previous demonstration up here, EasySpin just took the derivatives in order to kind of emulate the field modulation. All right, if you run this, it doesn't look much different. Maybe some of you saw a tiny little broadening, but if you now increase the field modulation a lot, let's say to 0.5 millitesla or 5 Gauss, you see that we're starting to distort the line shape. And this is called overmodulation. If your modulation amplitude is larger than your line width. And EasySpin can take care of that. Okay? So that's actually an important point. There is sometimes situations where you want to overmodulate in your experiment. For example, if you're really struggling for signal, overmodulation gives you a stronger signal, and this would allow you to measure weaker concentrations of your paramagnetic center. The good thing is now in EasySpin, you can just include this overmodulation in your simulation. So even though the spectrum is theoretically distorted, you can still perfectly simulate it. It's reproducible. So keep that in mind. So that is field modulation. Maybe the last thing we'll need to talk about in this session, how we're doing time-wise, yeah, is options, simulation options. As you've seen, Garlic, like any other simulation function, EasySpin, takes two inputs. The first input is the information about the sample, and the second input is the information about the experiment. Now, there can be a third input. And I'm going to just copy paste some settings from which I've prepared here, so I don't have to type it out. Here is a spin system, the G value of 2, 3 protons, each of them coupled with 78 megahertz. This is a mathematical, actually. X-band, 9.5 gigahertz with a lot of points, and we're going to look at the absorption spectrum. Let's run it. Voila. And what you can see is we have a stick spectrum. We should actually get, why do we not get the modulation here? Because maybe it's too small. It's a harmonic, oh, it's good. It's the absorption spectrum. So as you can see, we have an absorption spectrum with very narrow lines. Okay, now Garlic, like any other EasySpin simulation function, can take a third input argument, which are simulation options, traditionally called just opt. And one thing you can do is you can specify the simulation theory level in a field called method. And the first thing, the most important method, of course, is the exact method, and that's the one that's being used generally, right? And that's the default method. But you can also use perturbation theory. For example, perturb1 would be the first order perturbation theory. And then you can see the spectrum changes a tiny little bit. And if you go to second order perturbation theory, we'll see that now we'll get the second order splitting in the central lines here. Right? Let's go back to first order perturbation theory, perturb1. You can see we have 3 protons. And so you expect an intensity ratio of 1 to 3 to 3 to 1, as we see. That is kind of the simple splitting pattern. But as soon as you go to second order perturbation theory, you see that the 2 central peaks, they split into 2 separate peaks. You know, experimentally, these might not be easily resolvable for every system, but for mathematical, they are definitely resolvable. So we can also plot the 2 things in parallel. So we can just call B spec 1, this, and then we just copy paste this, and maybe just use the exact method and compare it to perturb1. And the exact method, let's call it spec 0, and just say plot B comma spec 0, B comma spec 1. Add a quick legend exact, and perturb1. Right, and there you can now see the comparison between the blue and the red spectrum. In particular, if you zoom in, you see that that's higher order splitting that comes in. So the red is an approximation, and the blue is the actual correct simulations, which EasySpin does by default. So there's a lot of options for these simulation functions. And the best way is just to look at them and find out about them looking at the documentation. And one section of the documentation that's really important is the function reference here. It contains a list of all EasySpin functions sorted by category, and also a separate list of all EasySpin functions in alphabetical order. Right? So if you want to find a specific function, or you want to figure out whether EasySpin has a function for a certain task, these two lists are the ones to look at. The most important core functions are listed here. And the first one, garlic, is what we looked at. If you click on that, you get the reference page for garlic, and it has the simulation options method, which we've looked at, and exact in a perturbation theory is implemented up to 5th order. And there's various other settings that can be adjusted. All right, this concludes session 3 about liquid state CW EPR. Please have a look at the script, glance at the exercises, maybe start them, or just take a break. If you have questions, head over to Slido and people will answer them. And I heard from, and I saw that lots of you are already contributing to answering the questions. Thank you so much. It's a great community effort. And see you in the next session, which starts in 9 minutes. Bye.